So, the next example that we consider is to find out the directional derivative of the determinant of A, okay, where A is a second order tensor in the direction u, which means when the tensor A is incremented by u, what is the change in the determinant of A. Okay. So, as you can see here, we can write the determinant of A plus u, okay, as determinant of A plus the directional derivative of A in the direction u. Okay. So, this directional derivative is what is the change in the value of the determinant when A is incremented by u. Okay. So, we start with our usual definition of finding the directional derivative, which is the directional derivative of determinant of A in the direction of u is nothing but d by d eta of determinant of A plus eta u. So, what we do? We replace A by A plus eta u. Okay. So, now unlike for scalar quantities, finding out the derivative with respect to eta is not that straightforward. So, the way we approach is, in the next step, okay, what we do is we take out this A outside the bracket. Okay. So, what it would become is A times I plus eta A inverse u. You can check for yourself. If you take A inside, you will get back this quantity over here. Okay. So, now we will invoke the property that determinant of A into P is nothing but determinant of A into determinant of B. For us, B here is I plus eta A inverse u. Okay. So, next step, when we invoke this relation, we can write determinant of A into determinant of I plus eta A inverse u. Okay. Now, determinant of A is independent of eta. So, it can be taken outside the bracket. Only the second term, okay, so the second determinant is dependent on eta. Okay. So, we have d by d eta of determinant of I plus eta A inverse u evaluated at eta equal to 0. Okay. Next, from the characteristic equation for second order tensor, we know that determinant of B minus lambda I, where lambda is the eigenvalue, can be written as lambda 1 minus lambda into lambda 2 minus lambda into lambda 3 minus lambda, where lambda 1, lambda 2, lambda 3 are the eigenvalues corresponding to B. Okay. So, if we compare this relation, okay, with determinant of I plus eta A inverse u. Okay. So, if we compare these two expressions, we can see that eta is or lambda is minus 1, okay, because the coefficient of I here and the coefficient of I here, you can check lambda is equal to minus 1 and B here is A inverse u, okay, is same as A inverse u. Okay. So, let lambda 1, lambda 2, lambda 3 be the eigenvalues of I plus eta A inverse u. Okay. So, we can substitute this expression here with the understanding that lambda 1, lambda 2, lambda 3 are the eigenvalues of I plus eta A inverse u. Okay. So, this is what we get, determinant of A into d by d eta 1 plus eta lambda 1 plus into 1 plus lambda eta 2 into 1 plus eta lambda 3, okay, where eta is the multiplier. Okay. So, eta was here. Okay. So, the eigenvalues of a matrix multiplied by a scalar, okay, will of a matrix multiplied by a scalar will be the scalar multiplied by the eigenvalues. Okay. So, the eigenvalues of eta A inverse u will be eta lambda 1, eta lambda 2, eta lambda 3, and that is what we have it here. Okay. So, now we can open up the bracket, you open up the first two brackets and this is what you are going to get. Okay. So, you open up first two brackets, you get this quantity and then you multiply this bracket with this bracket, you end up with this expression. Okay. 1 plus. So, you have a constant term, you have a linear term in eta, you have a quadratic term in eta and you have a cubic term in eta. Okay. So, once you have this, the next step is you take the derivative of this quantity in the bracket with respect to eta, okay, and this is what you get. The constant term does not have any eta, so it goes away. Okay. The constant term goes away, the linear term, all the etas go away. So, you are left with lambda 1 plus lambda 2 plus lambda 3. For the quadratic terms, you are left with 2 eta lambda 1 plus 2 eta lambda 2 lambda 3 plus 2 eta lambda 3 lambda 1, and for the last term you have 3 eta square lambda 1 lambda 2 lambda 3, and this you have to evaluate at eta equal to 0. When you substitute eta equal to 0, this term goes to 0 and this term goes to 0. Okay. So, these two last two terms drop off and you only, okay. So, last two no, I mean the last 4 terms drop off and only the first 3 terms remain, which is nothing but lambda 1 plus lambda 2 plus lambda 3. So, the directional derivative of determinant of A in the direction u is nothing but determinant of A multiplied by lambda 1 plus lambda 2 plus lambda 3. Remember, lambda 1, lambda 2, lambda 3 are nothing but the eigenvalues of the matrix A inverse u. So, we can simplify it little bit more. So, you would remember from our previous discussions that trace of a matrix can be written as sum of its eigenvalue. Okay. So, now we also have the sum of eigenvalues here, and these are eigenvalues corresponding to the matrix A inverse u. Okay. So, using this property we can write the term, the sum of the eigenvalues, that particular term as trace of the tensor A inverse u. Okay. So, now we have reduced the directional derivative of A in the direction u as determinant of A into trace of A inverse u. So, this can be simplified further if you remember the property of trace, okay, which is the trace of A into B, where A and B are two tensors, is nothing but A transpose double contraction with B. Okay. This is the property. Okay. So, once you remember this property, we can use it here. Okay. We can use it here to further reduce this expression on the right hand side to determinant of A into A inverse transpose contracted with u. Okay. So, finally, this is what we have derived, that the determinant of A, okay, the change in the value of determinant of A when A gets incremented by u is nothing but determinant of A into A inverse transpose double contracted with u. Okay. So, this is a very important derivation that we have done, and this will be used later on for our constitutive relations. Okay. One of the examples that we are going to discuss next also has this derivation, okay, this result used. Okay. So, once we have done this, we move to our next example, where we want to find out the directional derivative of inverse of a tensor in the direction of u. Okay. So, what we want to say is, if A gets incremented by u, what is the change in the value of A inverse? Okay. How much change is there? Again, first you can do the Taylor series expansion. So, A plus u inverse will be nothing but A inverse plus the directional derivative of A inverse in the direction of u. Okay. So, this second term is what is the change. Okay. Now, this directional derivative is what we now need to find out. Okay. So, again we can use the expression of directional derivative. So, the directional derivative of inverse of the tensor in the direction u is nothing but d by d eta of A plus eta u the whole inverse evaluated at eta equal to 0. Now, again this is a bit complicated to do. So, rather than proceeding directly from this point, what we do is, we first notice that for an invertible tensor, okay, invertible means for that tensor for which A inverse exists, we have this property A inverse is identity tensor, second order identity tensor. Okay. So, this is true, okay. And also the identity tensor is a constant tensor. Okay. So, if you remember the property of directional derivative, the second property that we discussed, that if g is a function, okay, nonlinear function, which is a function of product of two functions g1, g2, then the directional derivative of g at point x0 in the direction u was directional derivative of g1 at x0 in the direction u multiplied by g2 plus g1 multiplied by directional derivative of g2 evaluated at x0 in the direction u. Okay. So, this property we are going to use. Here our g1 is A and our g2 is A inverse. Okay. So, we are going to use this property. So, what we do? We take the directional derivative on both sides, okay, of this equation in the direction u. So, we have directional derivative of A inverse in the direction u is equal to directional derivative of I in the direction u. Okay. Now, the directional derivative of the identity tensor is 0, okay, second order 0 tensor, okay, because I is a constant tensor. So, it will not change if you increment the value of A by, I mean you increment the tensor A by u, there is nothing going to happen for I. Okay. So, therefore, using this on the right hand side, we get the directional derivative of A inverse in the direction u will be equal to 0. Okay. Now, using our property that we discussed in the previous slide, we will have the directional derivative of g1, which is A here in the direction u, times g2, which is A inverse, plus g1, which is A, times the directional derivative of g2 in the direction u. So, g2 is A inverse equal to 0. Okay. So, that is our, so if you look closely, this is our directional derivative that we wanted to find out. Okay. So, what we can do next is, we can take this term on the right hand side. Okay. So, this is what you are going to get. A directional derivative of A inverse in the direction u will be equal to minus of directional derivative of A in the evaluated at u times A inverse. Okay. If you pre-multiply both sides by A inverse and using A inverse equal to identity or A inverse A equal to identity, then so you multiply A inverse on both the sides, you will get our required expression for the directional derivative of inverse of a tensor in the direction u as nothing but minus of A inverse directional derivative of A in the direction u multiplied by A inverse. Okay. So, if A is a second order tensor and you increment A by u, then the change in the A inverse or the inverse of the tensor in the direction u will be nothing but minus of A inverse, the directional derivative of tensor A in the direction u, that is change of A in the direction u times A inverse. Okay. So, if you could find out the directional derivative or the change in the value of A in the direction u, you would be able to compute the change in the inverse of the second order tensor in the direction u. Okay. So, that is your final expression. So, you could see here we did not follow the usual route, that is d by d eta, computing d by d eta and then substituting eta equal to 0, but we proceeded in a different way. Okay. So, it is not always that you proceed in that particular sense. Okay. You have other means to derive the directional derivative. Okay. You have to be ingenious some of the time. Okay. Next, we come to finding the directional derivative of the inverse, okay, of a determinant of inverse of a tensor in the direction u. Okay. Suppose you change A to A plus u. So, we wish to determine what will be the change in the determinant of inverse of the tensor in the direction u. Okay. So, as you change A, its inverse also changes and therefore, its determinant also will change. So, we wish to determine how much the inverse of the determinant of inverse of the tensor changes. Okay. So, we can write the directional derivative, that is we want to find out the directional derivative of determinant of A inverse in the direction u is nothing but d by d eta evaluated at eta equal to 0 of determinant of A plus eta u the whole inverse. Okay. Now, we know that the determinant of the inverse of an invertible tensor is the inverse of the determinant of the invertible tensor, that is determinant of A into determinant of A inverse is 1. Okay. So, you also know from the matrix theory that determinant of a matrix time determinant of the inverse of that matrix is equal to 1. So, if you use this here, okay, so determinant of this tensor A plus eta u inverse will be nothing but 1 by determinant of A plus eta u. We have used this relation here. Okay. Now, we wish to compute. Okay. So, now what we do for this, you can write d by d determinant of A plus eta u, okay, and into 1 by determinant of A plus eta u evaluated at eta equal to 0 times d by d eta evaluated at eta equal to 0 determinant of A plus eta u. Okay. So, this term, okay, if you evaluate this term at eta equal to 0, you are going to get minus 1 determinant of A the whole square. Okay. So, you can just substitute determinant of A plus eta u as say x. So, this is like d by dx of 1 by x, which is nothing but minus 1 by x square. X here is determinant of a plus eta u, and then you have to evaluate that at eta equal to 0, and when you substitute eta equal to 0, you are left with determinant of a. So, the first term is minus 1 upon determinant of a the whole square, d by d eta of eta equal to 0, determinant of a plus eta u. Okay. So, determinant of a plus eta u is nothing but directional derivative of a, determinant of a in the direction u. This we have already computed. Okay. So, from our previous slides, okay, you can see that this term over here is nothing but the directional derivative of determinant of a in the direction u. And since we have already computed this, which was nothing but determinant of a into A inverse transpose double contracted with u. Okay. So, that is what we substitute here. Okay. So, substituting this, what you get? Minus 1 upon determinant of a the whole square, determinant of a into A inverse transpose double contracted with u. Okay. So, one determinant a cancels out, and then you have minus 1 by determinant of A inverse transpose double contracted with u. Okay. So, finally, you can, and now determinant of A is nothing but 1 by determinant of A inverse. Okay. So, 1 by determinant A. So, from here 1 by determinant of A will be equal to determinant of A inverse. Okay. So, that is what we substitute here, and then we get our required expression, which is the directional derivative of determinant of A inverse in the direction u is nothing but minus of determinant of A inverse into A inverse transpose double contracted with u. Okay. So, this is the change in the value of determinant of inverse of the tensor when the tensor itself gets incremented by u. Okay. So, when A gets incremented by u, that it becomes A plus u, then determinant of A inverse, the change in determinant of A inverse will be given by this quantity over here. Okay. So, moving on to our next example. Okay. So, the next three examples that we will do will come handy when we are discussing the constitutive relation for compressible hyperelastic material. Okay. In hyperelasticity, it will be very handy if you remember this proofs. Okay. So, there instead of deriving these proofs, we will directly use the results for what we will derive in the next three examples. So, the first examples asks us to show that the derivative of the first invariant of a second order tensor with respect to the second order tensor is a second order identity tensor. Okay. So, you are asked to show that d I upon d A will be equal to I, which is second order identity. So, to proceed, what we have to do is we will derive our required result using indicial notation. Okay. So, remember the trace of a second order tensor, okay, the first invariant is nothing but the trace of a second order tensor. So, I A is nothing but trace of A. Okay. And then in indicial notation, you can write that as A K K. Okay. So, this is nothing but A 1 1 plus A 2 2 plus A 3 3. Okay. So, because if you remember the rule for indicial notation, whenever an index is repeated twice, then a summation is implied unless until you have specifically said that the no sum rule is valid, because we have not written no sum rule, which means that a summation over k is already implied. Okay. So, trace of A can be written as A subscript k k. Okay. That is the first invariant of a second order tensor. Once we have this, we can write our given expression on the left hand side, the derivative of the first invariant of the second order tensor with respect to the tensor itself in equivalent indicial notation. Okay. So, we can write, okay, so I A is A k k. So, we have d A k k divided by d A I j. Okay. So, why I j? Because if you look on the left hand side, the left hand side happens to be a second order tensor. Okay. You have a denominator, in denominator you have a second order tensor. So, it is a second order tensor. So, there will be two free indices. Okay. So, therefore, we will have two free indices in our term, and then because they are free indices, they will occur only once. So, therefore, we should, for the other indices, we should have some other symbol. So, we have chosen k. So, we have d A k k by d A I j. Okay. Now, if you remember the expression for derivative of a tensor with respect to a vector, okay, or another second order tensor, you will notice that d A k k by d A I j will be nothing but delta k I. Okay. So, first index over here and first index over here gives you the first Kronecker delta, delta k I, and then the second index over here and the second index over here gives you the second Kronecker delta, delta k j. Okay. So, del A k d A k k by d A I j is nothing but delta k I, delta k j. Okay. We can use the substitution property, and using this substitution property, delta k I, delta k j. So, k is common. So, one of the Kronecker delta can be replaced. Okay. Say we choose the second Kronecker delta to stay, and then the k in the second Kronecker delta will get replaced by this I. Okay. So, eventually del d A k k by d A I j is nothing but delta I j, which in direct notation is nothing but the second order identity tensor. Okay. So, if we substitute this relation, okay, in this equation star over here, okay, we get the derivative of the first invariant of a second order tensor with respect to the tensor itself as the second order identity tensor. Okay. So, that is a very useful relation which will be used later when we are discussing the hyperelasticity. Okay. So, now you can establish the above result using directional derivative approach also. So, you can start with our usual definition of directional derivative and you can proceed. Okay. So, this is left as a task for you. Okay. The next example that we are going to consider, we want to show that the derivative of the second invariant of a second order tensor with respect to the tensor itself is nothing but the first invariant of the tensor multiplied by the second order identity tensor minus the tensor itself, where the second invariant of the tensor is given by following expression 1 by 2 the first invariant square minus A double contracted with A itself. Okay. So, that is a. So, again we start with indicial notation. Okay. So, when we start with indicial notation, yeah. So, remember it is I square. Okay. So, I square I A was A I I. Okay. See, on the left hand side you do not have any index, it is a scalar quantity. Okay. So, each of this product term or the symbol group. So, we have two symbol groups on the right hand side. Each of these symbol group will only have dummy indices or repeated index. There will be no free index. Okay. So, from our previous example, we know that the first invariant of a second order tensor can be written as AII or AKK, whatever index you choose. I choose specifically AII. Okay. Then IA square will not be AII square. Okay. So, that will be wrong to write if you write AII square. Okay. So, I told you that you should not write square of a tensor in indicial notation. Okay. So, this will not be true. Okay. So, if you have to write IA square, okay, what you have to do is you have to write IA into IA, and then you have AII. Now, for the second I, what do? See, there will be no free index, okay, and there will be only repeated index. Okay. So, the second I, okay, over here we have to choose some other index, because one repeated index also cannot occur more than twice. So, we already have I twice, so I cannot occur again. So, we take, instead of I, we take j. Okay. So, I square A will be nothing but AII AJJ. So, that is your first expression in the right hand side in initial notation. Now, we want to write A double contracted with A in initial notation, and if you remember, this was nothing but AIJ AIJ. Okay. So, once we have our second invariant in terms of the tensor in initial notation, okay, this expression we have, then in initial notation we can write the derivative of the second invariant of the tensor with respect to tensor as d I A 2A divided by d A K L. Why K L? Because our expression for the second invariant already has two i's and two j's. Okay. So, now in any given expression we cannot have more than two repeated index. So, then we have to choose some other symbol for subscript, and we have chosen K and L. Okay. So, you have d 2A by d A K L. So, next we can substitute the expression for the second invariant of a second order tensor in the numerator. Okay. So, that is what we have done. We can write d by d A K L of 1 by 2 A I I A J J minus A I J A I J. Okay. So, now you can take 1 by 2 outside the bracket, it is a constant term, and then you just have to take the derivative of this term inside the bracket with respect to K L. Okay. So, you can take the derivative inside and you can use the chain rule. Okay. So, you have d by d A I I d A K L into A J J into plus A I I into d A J A J J by d A K L. Okay. That is the first term when it is taken derivative with respect to A K L, and then the second term you have 2 A I J, Okay. There are two Aij, so it will be twice of Aij dAij by dAKL. Okay. Now, from our previous example, you can substitute the derivative of the terms in terms of Kronecker delta. Okay. All these terms can be written in terms of Kronecker delta. So, the first term, okay, here is delta I k delta I l A j j A I delta j k delta j l minus 2 I j delta I k delta j l. Okay. And next what you can do is use the substitution property of Kronecker delta. So, delta I k delta I l, okay, if you see here, delta I k delta I l will be nothing but delta k l. Okay. And then you have, okay, so you will have A I I A delta j k delta j l, which will be nothing but A I I delta k l, and because I is a dummy index, can be replaced by j. Okay. So, this becomes twice of A j j delta k l minus delta 2 A I j delta I k delta j l. They do not have any index which is common, but they will replace I here and j here. So, the first Kronecker delta will replace I with k, and the second Kronecker delta will replace j with l. So, that is what you will have 2 A L k. Okay. So, next this 2 gets cancelled out and you are left with, so you will be left with A j j delta k l minus A L k. Okay. Sorry, this will be k l. Okay. Okay. So, it will be A k l. So, there is a typo here, it will be A k l. Okay. So, A j j is nothing but the first invariant, which is I, delta k l is nothing but, okay, second order identity tensor, and A k l is nothing but A. Okay. So, writing in direct notation, you can write the derivative of the second invariant of a tensor with respect to the tensor as I A into second order identity tensor I minus A. Okay. So, next you can derive what will be the derivative of second order, second invariant of the tensor with respect to the tensor when you use following definition of the second invariant. So, remember the last term over here, instead of having A contracted with A, we have trace of A square. Okay. So, you will notice that instead of A here, you should get A transpose, but that is left as a task for you. So, next we move to our next example. Okay. So, this is going to be our final example. So, we want to evaluate the derivative of the third invariant of a second order tensor with respect to the second order tensor. Okay. We want to show that it is the third invariant of a second order tensor multiplied by A inverse transpose. Okay. So, we know that the third invariant of a second order tensor is given by determinant of A. Okay. Now, if you remember, we already have derived that the directional derivative of determinant of A in the direction u is nothing but determinant of A into A inverse transpose double contracted with u. Okay. So, I can write determinant of A as 3A. Okay. So, 3A into A inverse transpose double contracted with u. Okay. So, let us say this is equation star. Okay. So, next we can write, okay, and this is an important concept that you should very clearly understand, that the directional derivative of determinant of A in the direction u is nothing but the derivative of determinant of A with respect to the tensor A in the direction of u. Okay. In the direction of u means double contracted with u. Okay. So, how do we write this? So, this has parallels with how we compute the gradient. Okay. So, if you remember, the directional derivative of a scalar function, okay, at x 0 in the direction u was nothing but the gradient of the function times u, okay, dotted with u. Okay. So, you can write directional derivative of a scalar function, okay, field evaluated at x 0 in the direction u as gradient of f evaluated at x 0 dotted with u. Okay. So, when we extend this concept to second order tensor, okay, so we can write. So, if you see, this term over here is same as this quantity. Okay. So, therefore, we will have to have the gradient of something similar to gradient of f, which is nothing but, and our f is nothing but determinant of A. Okay. So, we will have the determinant of A, the derivative of determinant of A with respect to A, and instead of dot product, because these were vectors. So, we had a dot product, but because now we have a second order tensor, we have to take double contraction. Okay. So, it is a double contraction in the direction u, similar to this here. Okay. Now, once we have this, let us say this is equation prime. Okay. Now, we can compare equation star and equation prime. Okay. So, on the left hand side, you see we have directional derivative of determinant of A in the direction u. From equation star, this is nothing but the determinant of A into A inverse transpose double contracted with u, and from equation prime, okay, we have this as the derivative of the determinant of A with respect to the tensor A double contracted with u, and remember u here is a arbitrary vector. So, if we compare our equations star and equation prime, so you will get the derivative of the third invariant of a second order tensor with respect to the tensor double contracted with u is equal to the third invariant of the second order tensor A inverse transpose double contracted with u. Okay. So, after this double contraction, we have the same quantity on both the sides. Therefore, the quantity with which u is being contracted with should also be same. Okay. So, this quantity over here should be equal to this quantity over here. Okay. So, if we compare both the sides, we can write the derivative of the third invariant of a second order tensor with respect to the tensor itself is nothing but the third invariant of the tensor multiplied by A inverse transpose. Okay. So, this relation again is a very important relation which will be used later. So, I will again go back to the last 3 examples and we will see what results we got. Okay. So, let me move back to So, a tensor has 3 invariants I A, 2 A and 3 A. Okay. 1, 2, 3. Okay. So, the first derivative of the first invariant of the tensor with respect to the tensor itself is nothing but identity second order identity tensor. Okay. So, d I by d A is nothing but I. Okay. The second invariant of the tensor, okay, 2 A. So, the derivative of second invariant of the second order tensor with respect to the tensor itself is nothing but the first invariant of the tensor multiplied by the second order identity tensor minus the tensor itself. Remember, for this case your second order your second invariant has to be defined in this way. Okay. So, again instead of that expression for second invariant, if it is defined in this particular manner, okay, then the final relation will be different. You will notice that you will get I A I minus A transpose. Okay. So, it did not have a transpose here, but if you use this expression for your second invariant of the tensor, you will get transpose. Okay. And the derivative of the determinant of the tensor, which is the third invariant of the tensor with respect to the tensor itself, is nothing but the third invariant of the tensor multiplied by A inverse transpose. So, d I A by d A is I, d 2 A by d A is I A I minus A, and d 3 A by d A is 3 A inverse transpose. So, these 3 expressions should be very clear to you, because we are going to use these expressions very often in our later discussions when we are developing the constitutive relations for hyperelastic material, okay, which means relation between stress and strain. Okay. So, with this example we have come to the end of this part of discussion on tensors. Okay. So, for last 6 lectures we have been discussing about various aspects of tensor. Okay. We discussed how simple tensor operations can be written in initial notation, direct notation. We discussed about the eigenvalues, the invariants of the tensors. Then finally, we discuss what is meant by directional derivative and linearization and directional derivative of the second order tensor. And then we looked into how to compute the gradient divergence of second order tensor, first order tensors and scalars. Okay. And finally, we looked into one important integral theorem, okay, for scalars, vectors and second order tensors. And specifically, we saw the important theorem of Gauss divergence theorem. Okay. So, this theorem Gauss divergence will be again used later when we are deriving the when we look into the weak form. Okay. So, with this we have come to close for this part of the course, and next we will move to the next part of the course, which is on kinematics, that is where we consider deformation without actually considering the cause for that deformation, which means we will not take force into account and we will look into how the deformation can be characterized. Okay. So, we will close today and we will see you in the next module of this course, which will be on kinematics. Thank you.